Hi, welcome to Understanding Complex Exponentials, Lecture 7, Beats in Sound Waves. In this lecture, we will apply what we've learned so far about complex exponentials to sound waves. We'll add two sound waves of different frequencies together and see the interesting pattern that results, and we'll examine the resulting function graphically and see what it sounds like. So we experience sound when our eardrums vibrate. These vibrations are transmitted from whatever originally made the sound through the air to our ears. Most sounds we hear are made of very complicated vibrations, but pure tones are vibrations which have the form of a sine wave with a specific frequency. Higher frequency sine waves imply higher pitch in the sound we hear, and lower frequency gives lower pitch. Here we're going to get a first glimpse at how complicated sounds can arise by adding together pure tones. To see this, we'll add two sine waves together with slightly different frequencies. We'll see that the resulting function isn't a pure sine wave, but something more complicated. After we've gone through the math, we'll listen to two pure tones and the sound that results when we play them both at the same time. We'll see that the sound of the two combined tones has a structure that we can discern. And complex exponentials will be very helpful in this lecture. Okay, so here we're going to represent the vibration of our eardrum by a function that we will call f of t, where t is time. When f is positive, the center of our eardrum is displaced in one direction, say to the right, by a tiny amount. When f is negative, it is moved the other way, say to the left. If we are listening to a sound of a single frequency, f of t can be represented as a sine wave. So f of t equals a, which is some amplitude, times sine of omega t. And again, here t is time and omega is an angular frequency. Okay, so complicated sounds are made by adding different frequencies together. Here, we're going to look at what happens when the sound we hear is just the sum of two pure tones. We'll give them the same amplitude A. So our expression for f of t is equal to A sine omega 1t plus A sine omega 2t. Now let's see if we can get f of t into a form that's easier to visualize. Using our expressions for the sine function in terms of complex exponentials, we will rewrite each of the two sine functions that are inside f of t. So f of t is equal to the sum of these two sines, and that is equal to a times e to the I omega 1t minus e to the minus I omega 1t over 2I plus e to the I omega 2t minus e to the minus I omega 2t over 2I. Okay, let's take that expression and regroup the terms. So our f of t, which is this sum of two sine waves, is equal to a over 2I times e to the I omega 1t plus e to the I omega 2t minus e to the minus I omega 1t plus e to the minus I omega 2t. And note that we moved the 2i out front, and also we changed the order of the terms in parentheses. Okay, so from the previous slide we have our expression for f of t. Now let's define two quantities. The first quantity we'll call omega, and that's equal to omega 1 plus omega 2 over 2. The second quantity we'll call delta, and delta is equal to omega 1 minus omega 2 over 2. So note that omega 1 equals omega plus delta, and omega 2 equals omega minus delta. So now we can rewrite e to the I omega 1t as e to the I omega t, e to the I delta t. And we can write e to the I omega 2t as e to the I omega t, e to the minus I delta t. Okay, now we can rewrite f of t as a over 2i times e to the I omega t, e to the I delta t, plus e to the I omega t, e to the minus I delta t, minus e to the minus I omega t, e to the minus I delta t, plus e to the minus I omega t, e to the I delta t. Okay, so we have that expression from the previous slide. Now we can factor out e to the I omega t from the first term and e to the minus I omega t from the second term. So factoring out those factors of e to the I omega t and e to the minus I omega t gives that f of t is equal to a over 2i e to the I omega t times e to the I delta t plus e to the minus I delta t minus e to the minus I omega t times e to the minus I delta t plus e to the I delta t. Okay, so we have our expression from the previous slide. Note that there is a factor of e to the minus I delta t plus e to the I delta t in both terms. So let's use our relation that cosine of delta t is equal to e to the I delta t plus e to the minus I delta t over 2. So this means that e to the minus I delta t plus e to the I delta t is equal to 2 cosine delta t. So this lets us write f of t equals a over I cosine of delta t times e to the I omega t minus e to the minus I omega t. And now we can also use the relation that sine of omega t is equal to e to the I omega t minus e to the minus I omega t over 2i. And this gives that f of t is equal to a cosine of delta t times 2 sine of omega t, or 2a cosine delta t sine omega t. Okay, so let's look at that result. F of t, which we originally defined to be a times sine of omega 1t plus sine of omega 2t is equal to 2a times cosine delta t times sine omega t. We've managed to rewrite a sum of two sine waves into a product of a sine and a cosine. At first, this might not look so helpful, but a particularly interesting result occurs when omega 1 and omega 2 are very close to one another, but not equal. So when the absolute value of 2 delta, which equals the absolute value of omega 1 minus omega 2, is much less than omega 1, and when omega 1 and omega 2 and omega are all very, very similar to each other. Let's look at the situation where the absolute value of delta is much less than omega and see if we can understand the form of this expression. Okay, so from the previous slide we have our expression for f of t. First note that if omega 1 equals omega 2, we have delta equals 0 and omega equals omega 1 and omega 2. As the cosine of 0 equals 1, we just get that f of t is equal to 2a times sine omega t. And this makes sense. We added two identical sine waves together, and that's what we got out. Okay, now let's look at the case where 2 delta is not 0, but the absolute value of 2 delta is much less than omega 1, and omega 1 and omega 2 and omega are all very similar to each other. Here, we still get a factor of 2a sine omega t, but it's multiplied by a modulating function cosine delta t. Let's see this graphically. Okay, so let's plot two sine waves and their sum. So in red, we've plotted our f1 of t. It's the sine of 2 pi times 2t. In blue, we've plotted our f2 of t. So that's sine of 2 pi times 2.2t. And at the bottom, in black, we've plotted f of t, which is their sum. Now, near some values of t, the peaks in f1 of t approximately line up with the peaks in f2 of t. When this happens, the amplitude of f of t, which is their sum, is large. This is what is happening near the points t equals 0, t equals 5, and t equals 10. However, near some other values of t, the peaks in f1 of t approximately line up with the troughs in f2 of t. Then the two pieces largely cancel, and the amplitude of f of t is small. This is what is happening near t equals 2.5 and t equals 7.5. So the amplitude of f of t is large where f1 of t and f2 of t are in phase, and small where they are exactly out of phase. This modulation of the sine wave produces the phenomenon of beats. The volume of the sound is not constant, but instead has periodic structure. Let's see if we can hear this. We'll play 3 sounds. The first is a pure tone of frequency 440 Hz. Then we'll play one of 442 Hz. Lastly, we'll play them both at the same time. Okay, here goes. Did you hear it? If not, you might want to go back and try a few more times. Okay, let's summarize. In this lecture, we've introduced a topic from the physical world, beats in sound waves. We used complex exponentials to simplify our mathematical expressions and get them into a form where it was easier to see the important features of the results. We then saw the graphical interpretation of our expressions and tested them out using real sound waves.